Welcome, curious minds, to another deep dive. Today, we're tackling something really mind-bending. What if something could be incredibly hot, but at the same time kind of frozen in a quantum way? We're going deep into a breakthrough that really pushes the limits of what we thought was possible. We're talking about demonstrating quantum rotational vibrations.
In nanoparticles
Uh,
at room
yes,
temperature.
no extreme cooling needed.
Exactly.
And that's the core of it, really, because, usually seeing quantum effects, it's always been about getting things incredibly cold, like near absolute zero, minus 273.15 Celsius cold. So this research for this specific type of quantum behavior, it just turns that idea on its head. It's pretty significant. Absolutely. A real paradigm shift, potentially. So for this deep dive, we're looking at a SciTech Daily article. It reports on research from Nature Physics from a team at ETH Zurich and TU Wien in Vienna. So our mission today, let's unpack how they actually did this amazing thing. What does it mean for, how we understand the quantum world? And why might this be, a room temperature quantum revolution? Okay, let's unpack this. So the central discovery, scientists showed these tiny glass spheres exhibiting quantum rotational vibrations without cooling. You mentioned these spheres are about 100 nanometers across. How tiny is that really? And is that big or small for quantum?
That's a great point. 100 nanometers, well, it's 1,000 times smaller than a grain of sand. So tiny to us. But in the quantum world, that's actually pretty large. And normally, with objects that big, any quantum weirdness gets drowned out by noise from the environment. But the kicker here, like you said, the particles themselves, hundreds of degrees hot, yet their rotation was effectively in a quantum frozen state.
Wow. Okay, so what's going on here with these oscillation quanta and the whole discrete energy level thing in quantum mechanics? Can you break that down?
Sure. Think about a pendulum on a clock.
Mhm.
It can swing at pretty much any angle, right? A continuous range. But in the quantum world, especially at really low energies, it's different. Things happen in jumps, oscillations like spinning or wobbling happen in specific discrete amounts of energy. You have the ground state, that's the absolute lowest energy possible for that rotation. Then there's the first excited state, bit more energy, then a second, and so on. But nothing in between those levels. It's like specific channels on a radio, not a smooth dial. A particle can also be in a weird quantum mix of states at once, but the levels themselves are fixed. It's definitely not our everyday experience, right?
Not at all. Which leads to the big question. Why is this usually so difficult? Why the need for extreme cold normally?
Well, the main enemy is something called decoherence. The quantum world is incredibly fragile. Any little interaction with the outside world, a stray light particle, an air molecule bumping into it, can just destroy that delicate quantum state. Poof, it becomes classical. So you need extreme isolation. And cooling things way down is the standard way to minimize all that thermal jiggling and noise, to let the quantum effects, actually show up.
Right. Reduce the random motion.
Exactly. Which is why this new technique from ETH Zurich and TU Wien is so clever. They found a workaround for this specific quantum property, the rotation, without needing the fridge.
Okay, so how? How did they bypass the cold? What's the trick?
Okay, so they started with a nanoparticle that wasn't perfectly round. It was slightly elliptical, like a tiny egg shape. They held this particle in an electromagnetic field, which made it rotate. But here's the key bit. They used lasers, carefully tuned lasers and mirrors. The goal wasn't just to trap it, but to actively drain energy from its rotation. Carlos Gonzalez Balestro, one of the researchers, explained it well. He said the laser can give energy or take it away. By setting up the mirrors just right, they made it much more likely that the laser interaction would remove rotational energy rather than add it.
Ah, okay, so they're actively cooling just the rotation.
Precisely. They kept doing this, pulling energy out until the rotation got closer and closer to that quantum ground state, the lowest possible spin. And crucially, this wasn't simple. They had to figure out some complex theory too, like how to deal with the inherent quantum noise of the laser light itself. You have to control that randomness to make sure you're consistently sucking energy out, not accidentally adding it back in.
Okay, but here's where my brain starts to melt a little. They get the rotation down to its quantum ground state, like fundamentally frozen. Yet the nanoparticle itself is still sizzling hot, hundreds of degrees. How does that even work? It seems like a total paradox.
It does sound like one. But if we think about it, it comes down to what physicists call different degrees of freedom.
Hmm.
Think of maybe a spinning basketball that's also hot from being left in the sun. You could potentially stop its spin, right? Without instantly making the rubber itself cold. Here, they found a way to target just the energy of the overall rotational motion very effectively. They suck the energy out of that specific degree of freedom, the rotation, without significantly cooling the internal thermal energy. The random vibrations of the atoms inside the particle. That's what temperature really
So
measures.
the internal jiggling is still going wild, making it hot.
Exactly, but the overall rotation, the whole sphere, cooled down to the quantum limit. They separated those energy types. It's really elegant.
That car analogy helps too, like cooling just the wheel spin, not the engine temp. Does this idea of separating degrees of freedom, does that apply elsewhere in quantum?
Oh, absolutely. It's a really powerful concept in quantum control. This was rotation, but the principle applies. You could potentially target other specific quantum properties of a system without needing to cool the whole thing down.
Hmm.
It suggests a path towards more uh, surgical quantum manipulation, which is super valuable.
And this led to what they called record-breaking quantum purity. What does purity mean in this context? How close to perfectly quantum did they get?
Right? Purity. In quantum terms, it basically means how perfectly the system is in one specific quantum state. Like, is it at 100% in the ground state, or is it a messy mix of the ground state, maybe some excited states, and some thermal noise?
Ah, okay. Less noise, more purely quantum.
Exactly. High purity is critical if you want to reliably observe quantum effects or,
Yeah.
use them for something. And what they achieved here was getting this rotational state significantly pure, closer to that perfect quantum ground state than anyone had managed before for particles this size at room temperature, and without the big, expensive cooling systems.
So, okay, what does this mean going forward? This isn't just a cool lab trick, is it? What are the implications?
Definitely not just a lab trick. The paper calls it a technically astonishingly practical way to push quantum physics boundaries. Think about quantum sensors. Imagine sensors that could detect tiny forces or fields using quantum effects, but operating in normal conditions, not needing liquid helium.
Wow, okay.
Or maybe eventually components for quantum information processing that are more robust to temperature. It's
Yeah.
early days, but it broadens the horizon. It basically gives us a new, stable way to study quantum properties in these relatively large objects, which has always been incredibly difficult. It really pushes the boundary of how big something can be and still show quantum behavior without needing that extreme cold.
Right. So, just to kind of wrap things up for today's deep dive, we've explored this incredible feat where scientists used clever laser tricks with these elliptical nanoparticles. They managed to get the rotation of a hot particle into its quantum ground state, which sort of shatters that old rule that you always need extreme cold to see quantum stuff in objects this size, at least for this property.
Exactly, you've nailed it. By separating that rotational quantum state from the particle's internal heat, its thermal energy,
Mm-hmm.
it really does open up new ways to study quantum physics in a stable, reliable manner. It's a genuinely practical way to push those frontiers.
And that really leaves us with a big thought, doesn't it? For you, the listener, to ponder. If we can now start observing and controlling specific quantum effects in hot objects, what does that mean for the future? Could we see quantum technologies showing up in everyday places where we never thought possible? What other hidden quantum behaviors might be lurking in warm objects, just waiting for the right technique to reveal them?